One ordinary morning, you wake up and realize everything that was once considered valuable has suddenly lost its meaning. Not because of war, not because of a crisis, but because humanity has finally discovered a treasure that makes all previous treasures seem trivial. Billionaires, oil tycoons, gold mining empires, central banks, all of them suddenly find themselves in the same boat as Bronze Age blacksmiths. Their goods have become cheaper than sand. And the scariest part is that this isn't science fiction. It isn't sometime in the future. It's almost here. Right now, as you watch, a single object is quietly orbiting in the darkness between Mars and Jupiter. It doesn't shine. It has no atmosphere. It isn't even very large by cosmic standards. But its value is so absurd that the human brain literally refuses to process it. Not because you aren't smart enough, but because in your entire life, there has never been a reference point for such a number. No purchase, no paycheck, no news story has prepared you for this number. So now I ask you one thing. Don't let it pass you by, the way we usually let all big numbers pass us by. Try to feel it. Try to hold it in your mind. Because it's not just a curiosity, it's the most dangerous economic fact in the known universe. And it is right now at this very second about 370 million kilometers from where you are if you want to find out how a single asteroid could destroy the entire modern economy and what that means for each of us. Subscribe. There are even crazier numbers and an even scarier truth ahead. The number is 10,000 quadrillion dollars. Write it out and it looks like this. That headline figure still circulates widely, but it uses current Earth commodity prices. The moment extraction begins, those prices will collapse. More recent estimates place the realistic potential value in the tens of quintillions, still absurdly large but far from the original headline. That is a 10 followed by 19 zeros. That is 10 quintillion dollars. That is a number so far beyond the scale of normal human economic thinking that the word wealthy stops meaning anything in its presence. That is not a fortune. That is not a treasure. Those words are too small. That is something for which we do not yet have adequate language, because nothing in our history has ever required us to describe it. Let's try to make it real. Let's try to build a staircase from something you understand up to something you don't, one step at a time, until we're standing at the top looking down at the full, vertiginous drop. Start here. You are doing well for yourself if you have $100,000 saved. That's a good cushion. That's a year or two of financial security. $100,000 feels like real money to most people on this planet. Now multiply that by 10 and you have $1 million. That's the threshold where people start calling you wealthy, a millionaire. In most of the world, $1 million means you never have to worry about money again. You can own property, take care of your family, live comfortably for the rest of your life. $1 million is, by any reasonable human standard, a lot of money. Now multiply that million by 1,000. You have $1 billion. This is where it starts getting strange. $1 billion is not just a bigger million. It is a qualitatively different thing. If you spent $1 million a year, every year, it would take you 1,000 years to spend $1 billion. $1 billion means private jets and private islands and the ability to reshape institutions, fund political campaigns, build hospitals, change laws. There are roughly 2,800 billionaires on Earth right now. Each of them sits atop an almost incomprehensible pile of resources. And yet, in the context of the number we're working toward, $1 billion is essentially nothing. It is a rounding error. It is noise. Now multiply that billion by 1,000, you have $1 trillion. This is where language starts to fail us entirely. $1 trillion is more than the annual economic output of most countries on Earth. The entire gross domestic product of Australia, one of the wealthiest nations in the world, is about $1.7 trillion per year. $1 trillion is what the United States government spends roughly every 3 months. It is the kind of number that belongs to nation-states and central banks, not to individuals or companies. The richest person who has ever lived in the modern era, at the peak of their wealth, has approached but not reached $1 trillion. $1 trillion is the ceiling of human individual wealth. Nothing is ever broken through it. Now multiply that trillion by 1,000. You have $1 quadrillion. There is no human institution, no government, no economy, no concept in our financial system that operates at this scale. The entire global economy, every transaction, every salary, every stock trade, every real estate deal, every purchase of every cup of coffee by every person on every continent in an entire year adds up to approximately $100 trillion. A quadrillion is 10 times that. $1 quadrillion is more than all of human economic activity for an entire decade. It is, for all practical purposes, beyond the edge of meaning. Now multiply that quadrillion by 10,000. That is the number we're talking about. That is the estimated value of the metals contained in a single asteroid currently orbiting the Sun between Mars and Jupiter. That asteroid has a name. It is called 16 Psyche. And it is real. This is not science fiction. This is not speculation about some distant, hypothetical future where humanity has mastered the cosmos. This is a rock that exists right now, that astronomers have been studying for decades, that NASA has already launched a mission to visit. It is a confirmed catalog object with a known size, a known orbit, a known composition, and an estimated economic value that exceeds the combined wealth of every human being who has ever lived, multiplied by a number that itself resists comprehension. And here's the thing that should keep you awake tonight. We might be able to reach it, not in 1,000 years, not in some vague science fiction timeline, within the lifespan of people who are alive right now, within the professional careers of engineers who are working today, within the business plans of companies that have already been incorporated and are already raising money. Humanity might develop the capability to go to 16 Psyche and begin extracting what is there. The asteroid is not waiting for us to become a dramatically more advanced civilization. It is waiting for us to solve a set of engineering problems that are difficult but not impossible. Problems that look to people who work in the space industry roughly like the problems that faced early aviation pioneers in the 1900s. Hard, expensive, seemingly impractical, and then suddenly routine. When that happens, when the first drill bits or magnetic extractors or whatever tools we eventually develop make first contact with the surface of 16 Psyche, something will change about the human world that has never changed before in the entire history of our species. The fundamental assumption underlying every economy ever built, every war ever fought, every empire ever constructed, every trade route ever mapped, every slavery system ever enforced, every colonial project ever launched will be revealed as contingent rather than inevitable. That assumption is this: there is not enough. There is not enough iron. There is not enough nickel. There is not enough gold. Not enough platinum. Not enough of any of the metals that build our civilization and power our technology and give substance to our financial systems. That scarcity, that not enoughness, is the bedrock on which all of human economics is constructed. It is why things have prices. It is why people work. It is why nations go to war. It is why some people have almost everything and most people have almost nothing. The entire structure of human civilization, for all of recorded history, has been an elaborate response to the problem of scarcity. We have built governments and laws and markets and militaries all as mechanisms for deciding who gets the limited amount of stuff that exists. 16 Psyche does not care about any of that. 16 Psyche contains, in the iron and nickel and gold and platinum locked inside its metallic body, enough raw material to make the concept of scarcity, at least as it applies to these metals, functionally obsolete. The supply would be so vast, so unimaginably beyond current demand, that the very idea of these materials having a price in the way they currently have a price would require fundamental rethinking. Every commodity market, every metals exchange, every mining company, every nation whose economy depends on pulling ore out of the ground would be facing not a downturn, not a correction, not a crisis, but an extinction-level economic event. But before we get to what happens when this rock is cracked open, we need to understand what it actually is. Because 16 Psyche is not just a valuable rock, it is something stranger than that. Something that, the more you learn about it, starts to feel less like a random piece of space debris, and more like a message from the early solar system, a relic from the violent, chaotic birth of the worlds, a fragment of something that was almost a planet and never quite made it. Understanding what 16 Psyche is requires going back, not just decades, not just centuries, but 4.5 billion years, to a time before Earth had fully formed, before the sun had settled into the steady middle-aged star it is today, before the solar system was anything other than a churning disk of gas and rock and metal and possibility. 16 Psyche is, in a very real sense, a piece of a dead world, or more precisely, a piece of a world that never got to live. The story of how that happened, and why it left behind an object worth more than everything humanity has ever built or earned or stolen or traded in the entirety of our existence, is where this journey actually begins. And it starts, like all the best stories, with a collision so violent, so total, so absolutely final, that what was once on its way to becoming a planet was reduced to its naked metallic core, stripped of everything else, left spinning alone in the dark between Mars and Jupiter, waiting for a species smart enough and greedy enough and reckless enough to come looking for it. That species is us, and we are on our way. Here is something that should genuinely unsettle you. Somewhere inside the Earth, roughly 6,400 kilometers beneath your feet, there is an iron-nickel core the size of Mars. It contains the vast majority of the heaviest, most valuable metals on the planet. The gold, platinum, the iridium, the nickel. When Earth was young and molten, these dense metals sank. Gravity pulled them down through the liquid rock toward the center, where they have remained ever since, completely unreachable, locked behind thousands of kilometers of solid mantle. The deepest hole humanity has ever drilled is about 12 kilometers. We gave up. The metals we actually want, the metals that built our civilization and now power our technology and define our financial systems, are sitting at the center of our own planet, and we cannot get to them. We never will. 16 Psyche is what happens when you can. To understand why, you need to go back 4.5 billion years to a solar system that was still being assembled from the disk of gas and dust and metal left over after the sun ignited. In the region we now call the asteroid belt, rocky bodies were forming the same way Earth was forming, accumulating mass, generating internal heat from radioactive decay and constant impacts, growing large enough to melt internally and begin differentiating. That critical process where density sorts everything out. Heavy metals sink to the center. Lighter rock floats to the surface. You end up with a layered structure, a metallic core wrapped in a rocky mantle wrapped in a rocky crust. the same egg structure Earth has. These bodies were on their way to becoming planets. Then Jupiter ruined everything. Jupiter's gravitational influence turned the asteroid belt into a demolition derby. Objects that had spent millions of years carefully accumulating mass were slammed into each other at velocities high enough to destroy rather than merge. The differentiated bodies, the ones that had already developed their layered structure, were cracked open. Rocky crusts and mantles were blasted away into debris, and what remained, tumbling alone in the wreckage, was the densest part, the part that survived because it was the hardest to destroy, the metallic core. 16 Psyche is one of those cores. It is the exposed heart of a planetesimal that formed, differentiated, and was then stripped of everything surrounding it by one or more catastrophic collisions billions of years ago. What you are left with is an object roughly 280 kilometers wide, irregular and lumpy, shaped somewhat like a potato, orbiting the Sun in the main asteroid belt at a distance of about 437 million kilometers from the Sun. Its surface gravity is 1.4% of Earth's. You could jump several meters and drift slowly back down. A hard enough throw could put a baseball into orbit around it. A slightly harder one sends it into space entirely. For most of the 170 years since its discovery in 1852 by Italian astronomer Annibale de Gasparis, 16 Psyche was just a catalog entry. Object number 16, one rock among hundreds of thousands. What changed everything was radar. When astronomers bounced radio waves off its surface and analyzed what came back, the reflectivity signature was not that of a rocky asteroid. It was consistent with metal, dense, conductive, largely iron-nickel metal. Subsequent spectroscopic analysis found signatures consistent with iron, nickel, and potentially gold and platinum group elements, the same metals that on Earth sank to the core during differentiation and have been inaccessible ever since. On 16 Psyche, there is nothing on top of them. No crust to drill through, no mantle to penetrate. The treasure is the surface. NASA recognized something beyond economics immediately. If 16 Psyche really is an exposed planetary core, it is the only one within reach of human instruments anywhere in the known solar system. Every other differentiated rocky body in the solar system, every planet, every large moon has its core buried under layers of geology we cannot penetrate. 16 Psyche is a window into a type of interior that we have never directly observed. This is why the NASA Psyche spacecraft, launched in October 2023, is currently on its way. It will perform a gravity assist at Mars in May 2026 and is scheduled to arrive at the asteroid in August 2029, where it will spend roughly 2 years mapping the surface and studying its composition. The spaces alone would make this one of the most important missions in the history of planetary exploration. The legal framework for who can claim what in space remains underdeveloped and full of gaps. But science is not the whole story, not even close, because while NASA was designing a spacecraft to study 16 Psyche, other people were designing something different, not instruments for observation, equipment for extraction. The distinction matters enormously. One group wants to understand what 16 Psyche is. The other group wants to own it. In 1532, a Spanish conquistador named Francisco Pizarro arrived on the western coast of South America with 168 men, 27 horses, and 1 cannon. What he found was the Inca Empire, a civilization of somewhere between 10 and 12 million people, stretching 4,000 kilometers along the spine of the Andes, with a sophisticated road network, a complex administrative system, a military that had conquered most of the western continent, and an emperor named Atahualpa who had never heard of Spain and had absolutely no reason to consider 168 foreign men a threat to anything. Within 2 years, the Inca Empire was gone. Atahualpa was dead, strangled after paying a ransom of a room filled with gold and 2 rooms filled with silver, a ransom Pizarro accepted and then executed him anyway. The gold and silver were melted down, loaded onto ships, and sent to Spain. The civilization that had produced it was dismantled, its people enslaved, its institutions destroyed, its knowledge lost. What motivated all of this was not hatred. It was not ideology. It was not religion. The religion was used as justification. What motivated it was the thing that has motivated almost every act of large-scale organized human violence in recorded history. There was something valuable somewhere. Someone else had it, and the someone else was not strong enough to stop what happened next. This pattern is so consistent across human history that it barely qualifies as a pattern anymore. It is closer to a law, wherever valuable resources have been discovered in places where the existing power structures were either absent or insufficient to protect them. The sequence of events that followed has been remarkably similar regardless of the century, the geography, or the technology involved. First comes discovery. Then comes the realization of value. Then comes the rush, the chaotic scramble of early movers trying to establish position before the rules solidify. Then come the rules, written by whoever won the scramble, designed to protect what they have already claimed. And finally comes the long aftermath, the period of extraction and consolidation that can last centuries, during which the wealth flows in one direction while the costs are distributed in another. The Americas and their silver and gold. West Africa and its people, exported as labor to work the mines and plantations of the New World. The Middle East and its oil, carved into spheres of colonial influence by European powers who drew the borders specifically to keep the locals divided and dependent. The Congo and its rubber, then its copper, then its cobalt. Each successive resource boom leaving the country poorer and more damaged than the one before. The pattern does not require malice in the individuals involved, though malice is often present. It requires only the coincidence of enormous value, insufficient protection, and human beings who are very good at rationalizing why the rules that normally apply do not apply in this particular case. Now look up. Look past the atmosphere, past the moon, past Mars, out to the asteroid belt where 16 Psyches orbiting the sun right now. And ask yourself whether you see anything different about the situation, whether there is anything about the structure of the story, the discovery of enormous value in a place where existing power structures do not yet apply, that differs in any fundamental way from the stories that have played out on Earth for the past 500 years. The honest answer is not much. The technology is new. The location is new. The distances involved are new. But the logic is identical, and the people running the logic are not fictional characters from a dystopian novel. They are real companies, incorporated under real laws, raising real money from real investors, with real engineers working on real problems. The asteroid mining industry is not a future industry. It is a present one, in the early and chaotic phase that all industries inhabit before they become legible and regulated and boring. Planetary Resources was founded in 2012 by a group that included Peter Diamandis and Eric Anderson, backed by investors including Larry Page and Eric Schmidt of Google and filmmaker James Cameron. Its stated goal was to mine near-Earth asteroids for water and precious metals. It raised tens of millions of dollars, built a small telescope satellite called Arcade 3, launched it successfully, and then ran out of money and was acquired in 2018 by a blockchain company called Consensus, which had no particular interest in asteroid mining, but valued the intellectual property, Planetary Resources effectively ceased to exist as an asteroid mining company. Deep Space Industries was founded around the same time with similar goals, raised similar early investment, built similar early hardware, and was acquired in 2019 by Bradford Space, pivoting away from mining entirely. The first wave of asteroid mining companies did not succeed, but failure in the early phase of a new industry is not evidence that the industry is impossible. It is evidence that the early phase is difficult. The first wave of commercial aviation companies mostly failed too. The first wave of commercial internet companies failed so spectacularly that it generated a cultural shorthand, the dot-com crash, a byword for irrational exuberance. And then after the failure and the consolidation and the learning, aviation became the system that moves 4 billion passengers a year, and the internet became the infrastructure of the entire global economy. The second wave of asteroid mining companies is different from the first in one crucial respect. The first wave was founded on the premise that they needed to build everything from scratch, that no infrastructure existed, and they would have to create it entirely themselves. The second wave is being founded in a world where SpaceX has demonstrated reusable rockets, where launch costs have dropped by roughly 90% over the past decade, where small satellite technology has matured to the point where a serious space instrument can be built for millions rather than billions of dollars, and where the general trajectory of private space development suggests that costs will continue to fall. Astroforge, founded in 2022, remains one of the most visible players. Its first deep space test mission, Odin, launched in February 2025, but lost contact shortly after reaching deep space. The company is now preparing its next mission, Deep Space 2, or a Vestry, scheduled for launch in 2026. Vestry aims to be the first private spacecraft to land on an asteroid beyond Earth's gravity. Well and test platinum group metal prospecting, Karman Plus, Transastro, Origin Space, and several others are in various stages of development with various focuses within the asteroid mining value chain. These companies are not waiting for 16 Psyche specifically. The economics of getting to 16 Psyche, which orbits in the main asteroid belt at distances that require years of travel time, are currently prohibitive. The more immediately interesting targets are near-Earth asteroids, objects whose orbits bring them relatively close to Earth, making them far cheaper to reach. There are over 30,000 known near-Earth asteroids. Several hundred of them have been identified as economically interesting from a mining perspective. Some are rich in water ice, which can be split into hydrogen and oxygen to make rocket fuel, potentially enabling a fuel depot economy in space that would change the economics of deep space travel entirely. Some are rich in platinum group metals, elements so rare on Earth's surface that the global annual production is measured in hundreds of tons, elements whose price is high enough that even a relatively small asteroid could represent billions of dollars in value at current prices. But the legal situation surrounding all of this is, to put it charitably, a mess. The foundational document of space law is the Outer Space Treaty of 1967, signed during the Cold War by the United States, the Soviet Union, and most other spacefaring nations. The treaty established several principles that seemed sensible and uncontroversial at the time, when the idea of commercial resource extraction in space was pure science fiction. It declared that outer space is the province of all mankind. It prohibited national appropriation of the moon or other celestial bodies by claim of sovereignty, by means of use or occupation, or by any other means. It established that nations are responsible for the activities of their private citizens in space. What it did not do, because in 1967 it seemed unnecessary to do so, was say anything specific about whether a private company could land on an asteroid and take stuff from it. This gap has become the central legal question of the emerging space resource industry. The United States addressed it, at least domestically, with the Commercial Space Launch Competitiveness Act of 2015, which explicitly grants American citizens the right to own resources they extract from space, while stopping short of claiming sovereignty over the celestial bodies themselves. The distinction the law attempts to make is between owning a thing and owning a place. You cannot claim the asteroid, but if you land on it and take something, what you take is yours. Luxembourg passed similar legislation in 2017, making itself the first European country to establish a legal framework for space resource ownership, specifically in order to attract asteroid mining companies to incorporate there. The United Arab Emirates, Japan, and several other countries have followed with their own versions of similar frameworks. But here is the problem. These laws are national laws. They apply to companies and citizens within those jurisdictions. They do not bind anyone else. A company incorporated in a country that has not passed such legislation, or a country that interprets the Outer Space Treaty differently, is not obligated to recognize them. China, which has the second most capable space program on Earth and ambitions in space resources that are explicit in its national space policy, has not agreed to these frameworks. Russia has not agreed to them. The legal scaffolding that the United States and its allies are building around space resource extraction is scaffolding that only some of the relevant parties are standing on. What this means in practice is that if a company from one country lands on an asteroid and begins extracting resources, and a company from another country lands on the same asteroid and also begins extracting resources, there is currently no universally agreed legal mechanism for resolving the conflict. There is no space court. There is no space police force. There is no body with both the jurisdiction and the enforcement capability to tell one party to stop and make it stick. What there is precedent. The precedent of whoever gets there first establishes operations first and is backed by a national government powerful enough to defend the claim politically, if not militarily. This is again the oldest story in the world. The flag gets planted, the claim gets made. The rules get written around the claim by whoever planted the flag. And then the rules get called natural and inevitable and universal by the people who wrote them, and unjust and illegitimate by the people who didn't get there in time. This sequence has repeated itself so many times in human history that the surprise would be if it did not repeat in space. The surprise would be if this time, with this resource, with these stakes, human beings collectively decided to do something different, something more cooperative, more equitable, more far-sighted than the pattern that has defined every previous resource frontier. History does not give us strong reasons to expect that surprise, but technology might, because the technology required to get to an asteroid and extract its resources is not simple, and the entities that can realistically develop it in the near term are not rogue actors operating in secret. They are large, visible, well-capitalized companies operating in public, raising money from public markets, subject to at least some regulatory oversight. The Wild West phase of asteroid mining, if it comes, will be a Wild West visible from Earth, documented in real time, with investors and journalists and governments watching. That visibility creates at least the possibility of intervention, of rulemaking, of the kind of multilateral negotiation that shapes the frontier before the damage is done, rather than after. Whether that possibility becomes reality depends on whether the governments and international institutions responsible for space law can move faster than technology. Whether they can write the rules before the flag gets planted, rather than scrambling to catch up afterward. So far, they are not moving fast. Technology is not waiting for them. And somewhere in the asteroid belt, 16 Psyche continues its slow orbit around the sun, indifferent to the legal debates and investment memos and geopolitical calculations being conducted in its name. It has been orbiting for 4.5 billion years. It will orbit for billions more regardless of what humanity decides to do about it. But what humanity decides to do about it, the choices made in the next few decades about who goes, who owns what they find, and what rules govern the process, will determine something far more consequential than the fate of one asteroid. They will determine whether the next chapter of the oldest story in the world ends the same way all the previous chapters have, or whether, this time, we manage to write a different ending. Before we can think about endings, we need to understand the middle, the part that comes between ambition and the outcome, the part that the investment decks and the legal white papers and the political speeches never quite get around to explaining in adequate detail, the part where someone actually has to figure out how to get there, how to land on a spinning metallic rock in the vacuum of space, hundreds of millions of kilometers from the nearest hardware store, and begin pulling metal out of it in quantities large enough to matter, without killing everyone involved, without spending more than the metals are worth, and without creating a debris field that makes the entire asteroid belt a navigational hazard for the next 1,000 years. Engineering. The actual unglamorous, physics-constrained, budget-limited, failure-prone engineering that stands between the dream of asteroid mining and the reality of it. That is where we are going next, and it is harder than you think. Let's start with something simple, something so obvious it sounds almost insulting to say out loud. Before you can mine an asteroid, you have to get to it, and getting to things in space is nothing like getting to things on Earth. On Earth, distance is the primary obstacle. You want to go somewhere far away. You need time and fuel proportional to the distance. Space does not work like that. In space, distance is almost irrelevant compared to the real obstacle, which is velocity. Specifically, the change in velocity required to get from where you are to where you want to be. Engineers call this delta V. It is the single most important number in all of spaceflight, the number that determines whether a mission is possible, how much it costs, how long it takes, and how much you can bring with you, and it behaves in ways that are deeply counterintuitive to anyone who has spent their entire life moving around on the surface of a planet. Here is the counterintuitive part. The moon is roughly 384,000 kilometers from Earth. Mars, at its closest, is about 55 million kilometers away. Mars is therefore roughly 140 times farther from Earth than the moon. By Earth logic, going to Mars should require roughly 140 times more fuel than going to the moon. It does not. It requires only about twice the delta V. Distance in space is almost a distraction. What matters is the gravitational landscape you have to navigate, the wells you have to climb out of, and the wells you have to descend into, the orbital mechanics that determine how much energy a particular journey actually costs, regardless of how far away the destination looks on a map. This is relevant to asteroid mining because some of the most economically interesting asteroids are not the ones that are physically closest to Earth. They are the ones that are cheapest to reach in terms of delta V. And the delta V map of the solar system has some surprising features. Certain near-Earth asteroids are actually easier to reach in terms of fuel cost than the surface of the moon. The moon is close, but it sits at the bottom of a significant gravitational well. You have to burn a lot of fuel to land on it and more fuel to take off again. Some asteroids orbit in configurations that require relatively modest velocity changes to reach from Earth orbit. And because they have almost no gravity of their own, you do not need much fuel to land on them or leave them. In delta V terms, they are cheap destinations. Cheaper than our nearest neighbor in absolute distance. The asteroids that are hardest to reach in delta V terms are the ones in the main belt, where 16 Psyche lives. Getting to 16 Psyche from Earth requires a delta V of roughly 8 to 10 kilometers per second, depending on the trajectory and the launch window. For context, getting to low Earth orbit from the ground requires about 9.4 kilometers per second. Getting to the Moon's surface requires about 6 kilometers per second from Earth orbit. Getting to 16 Psyche is roughly equivalent, in fuel terms, to launching from Earth to orbit and doing it again. It is not impossible, but it is expensive, and the journey takes years, not days. The NASA Psyche spacecraft, launched in October 2023, will not arrive until 2029. 6 years of travel. And the spacecraft is not carrying mining equipment. It is carrying scientific instruments that weigh a fraction of what any serious extraction operation would require. This is the first engineering reality of asteroid mining. The destinations that are most valuable in terms of raw material are not necessarily the easiest to reach, and the vehicles required to reach them carrying useful payloads do not yet exist. The rocket equation, that cruel mathematical relationship between payload mass, fuel mass, and delta V, means that every kilogram of mining equipment you want to deliver to a distant asteroid requires multiple kilograms of fuel to get it there, which requires more fuel to carry the fuel, which requires more fuel to carry that fuel. The rocket equation does not care about your business plan. It is one of the most unforgiving constraints in all of engineering, and it has humbled smarter people than the investors currently funding asteroid mining startups. So how do you actually do this? The honest answer is that nobody has done it yet at commercial scale, and the specific approach depends enormously on what you are trying to extract. From what type of asteroid, at what distance, for what purpose. The engineering challenges are not one problem. They are a nested sequence of problems, each of which must be solved before the next one becomes relevant, and each of which contains its own sub-problems that become apparent only when you get close enough to confront them directly. This is the nature of genuinely novel engineering. You do not know what you do not know until you are already there. But we can lay out the main chapters of the problem clearly enough. The first chapter is rendezvous. Getting your spacecraft to the same place as the asteroid at the same time, moving at the same velocity, close enough to do something useful. This sounds straightforward and is not. Asteroids are not stationary targets. They are moving at speeds of tens of kilometers per second relative to the Sun, in orbits that are often inclined relative to the ecliptic plane, frequently tumbling or rotating in ways that are only approximately known from ground-based observations. The tumble rate of 16 Psyche, for instance, is about 4 hours and 12 minutes per rotation. That means the surface is constantly moving. A feature that is in sunlight and accessible when you arrive might be in shadow or facing away from you 4 hours later. Planning any surface operation requires accounting for this rotation continuously, not as a fixed backdrop but as a moving variable that affects everything from power generation to communication to the mechanics of landing itself. Rendezvous with a small, low-gravity, rotating body is a solved problem in the sense that it has been done before. The Japanese Hayabusa mission successfully sampled 2 asteroids, Itokawa in 2005 and Ryugu in 2019, returning material to Earth. NASA's OSIRIS-REx mission successfully collected a sample from asteroid Bennu in 2020 and returned it to Earth in 2023. These missions prove that it is possible to navigate to an asteroid, match its velocity and rotation, approach its surface carefully, and interact with it. What they did not prove is that you can do this with mining equipment instead of scientific instruments, or that you can do it economically, or that you can do it repeatedly at industrial scale without human operators making real-time adjustments from hundreds of millions of kilometers away. The second chapter is proximity operations. Once you are near the asteroid, you need to stay near it without crashing into it, without drifting away from it, and without being disturbed by the various forces that act on a spacecraft in close proximity to a small body. This is more complicated than it sounds because the gravitational field of a small, irregularly shaped asteroid is itself irregular. It does not behave like a simple sphere. It has lumps and voids that create local variations in gravitational pull. At very low altitudes, the gravitational field can be almost chaotic, with regions of net outward force rather than inward pull because the asteroid shape creates more gravitational attraction from the sides than from below. Solar radiation pressure, the gentle but persistent push of photons from the sun, is significant enough relative to the weak gravity of a small asteroid to meaningfully perturb a spacecraft's orbit. Outgassing, the release of volatile materials from the surface when heated by sunlight, can create tiny but real thrust forces. All of these effects must be continuously modeled and compensated for. The navigation problem near a small asteroid is orders of magnitude more complex than the navigation problem in open space. The third chapter is extraction, and this is where the engineering gets genuinely strange, because almost everything you know about mining is wrong in the context of an asteroid. On Earth, mining works by using large, heavy machines powered by diesel or electricity, which use the downward force of gravity to drive cutting tools into rock, then use conveyors and trucks and trains to move the extracted material from the mine to the processing facility. Every part of this system depends on gravity. The machines stay on the ground because gravity holds them there. The material falls down the chute because gravity pulls it. The trucks drive on the road because gravity keeps them on it. Remove gravity and the entire conceptual framework of mining collapses. On an asteroid with surface gravity 1.4% of Earth's, like 16 Psyche, a mining machine cannot simply sit on the surface and do its work. The vibration from its own cutting action would tend to push it off the surface. The reaction force from drilling into metal would push it away from the metal. Extracted material, instead of falling into a hopper, would drift away in whatever direction it was moving when it left the surface, potentially achieving escape velocity, which on 16 Psyche is only 180 meters per second, and floating off into space as a small debris cloud. The mining machine itself, if not carefully anchored, would drift off the surface and become an uncontrolled object tumbling slowly away from the asteroid. Anchoring is its own nightmare. You cannot use gravity anchors because there is no meaningful gravity. You cannot drive stakes into the surface because the reaction force of hammering the stake pushes you away. Proposed solutions include threaded anchors screwed into the surface, which requires first drilling a pilot hole, which requires first anchoring to drill the pilot hole. A circular problem. Magnetic anchors work only if the surface is sufficiently magnetic, which for an iron-nickel asteroid like 16 Psyche is actually plausible, making it better suited to magnetic anchoring than most asteroid types. Harpoon-style anchors fired into the surface and then retracted under tension have been tested by the Hayabusa missions with mixed results. Mascot, a small lander deployed by Hayabusa 2 to asteroid Ryugu, bounced several times on the surface before coming to rest because the surface was too soft and irregular for its landing system to grip. Then there is the question of what you are actually cutting. 16 Psyche is not rock, it is metal. Dense, hard, iron-nickel metal, the kind of material that on Earth requires industrial-grade cutting tools and significant force to machine. The exact hardness and structure of Psyche's surface is unknown because no mission has yet touched it. It may be solid metal, or it may be a regolith, a layer of fine metallic grains created by billions of years of micrometeorite impacts pulverizing the surface, mixed with larger fragments. If it is regolith, collection might be relatively easy. You could scoop it or use a gas jet to loft it into a collection bag. The approach used successfully by both Hayabusa missions and OSIRIS-REx. If it is solid metal, you need cutting tools capable of machining iron-nickel in vacuum. at temperatures that swing between -188 and +100 degrees Celsius, depending on whether you are in sunlight or shadow, powered by solar panels that are already carrying the weight and complexity of the extraction system. The power problem is significant. Industrial mining is energy intensive by nature. Solar power at the distance of the asteroid belt, where 16 Psyche orbits, is about 30% of what it is at Earth's distance from the Sun. The solar panels required to power serious extraction equipment at that distance would be enormous, adding mass that must be launched from Earth, increasing cost, creating more surface area vulnerable to micrometeorite damage, and complicating the spacecraft's dynamics. Nuclear power, specifically small fission reactors of the type NASA has been developing under programs like Kilopower and its successor fission surface power, is the more likely solution for serious deep space industrial operations. The United States successfully tested a working space fission reactor concept in 2018. Actual deployment in space remains unlicensed and untested in the current regulatory environment. And then there is the question that the engineering papers do not always address as directly as they should. After you extract the material, what do you do with it? If the goal is to return metals to Earth, you have to launch them from the asteroid, navigate them back across hundreds of millions of kilometers, decelerate them into Earth orbit without burning them up, and then deliver them to a market that, as we will discuss in considerable detail shortly, may not look anything like the market you planned for when you started the mission. The mass you can realistically return to Earth on any near-term mission is modest. The Hayabusa 2 mission returned 5.4 grams of material from Ryugu. OSIRIS-REx returned about 121 grams from Bennu. These are scientific triumphs. They are not economic models for a profitable mining operation. A viable commercial return mission would need to bring back tons, not grams, potentially thousands of tons to justify the cost of the mission. The engineering required to do that is not a small extrapolation from what has been demonstrated. It is a qualitative jump to a different class of capability. This is why many of the more thoughtful people in the asteroid mining industry have concluded that the early economic model is probably not Earth return at all. It is in space use. Mine the asteroid, process the material in space, use the processed material in space to build structures, manufacture components, or produce rocket propellant. The water-rich asteroids are particularly interesting in this context because water can be electrolyzed into hydrogen and oxygen, the same propellants used by some of the most powerful rocket engines ever built. An asteroid mining operation that produces rocket fuel in space at a location where spacecraft traveling beyond Earth orbit could refuel would change the economics of the entire space economy by removing the need to lift every gram of propellant from Earth's surface. This is sometimes called a propellant depot economy, and if it becomes real, it makes everything else in space dramatically cheaper and more accessible. This is the current state of asteroid mining, not the science fiction of automated industrial operations at 16 Psyche, not the investment pitch version where the numbers are large and the obstacles are briefly noted before being dismissed. The real version, which is a collection of genuinely difficult engineering problems being worked on by relatively small teams with limited budgets, making real progress, demonstrating real capabilities, while being honest, at least among themselves, about how large the gap remains between where they are and where they need to be. The gap is real. But the prize, tens of quintillions in potential value, is large enough that the gap will close. Not tomorrow, but within the professional lifetimes of engineers working today. And when it does, the engineering problem will be solved. The economic problem, however, will only just be beginning. In 1545, a Quechua llama herder named Diego Hualpa was climbing a mountain in what is now Bolivia when he noticed something unusual about the rock beneath his feet. It was silver, not traces of silver, not a promising seam worth investigating. An entire mountain, Cerro Rico, rich mountain, containing what turned out to be one of the largest silver deposits ever discovered on Earth. Within a decade, the Spanish colonial machine had descended on it with full force. Within a century, Potosí, the city that grew at the mountain's base, had become one of the largest cities in the world, larger than London, larger than Paris, producing roughly half of all the silver circulating in the global economy. Ships crossed the Atlantic loaded with it. Empires were financed by it. Wars were fought over the trade routes it traveled. And then something strange happened. Something that the Spanish crown, despite its considerable political and military sophistication, had entirely failed to anticipate. All that silver, flooding into the European economy in quantities that dwarfed anything previously available, began destroying the very economy it was supposed to enrich. Prices across Europe rose dramatically over the 16th and 17th centuries in what historians now call the price revolution. When the supply of money increases faster than the supply of goods, the value of the money falls. Each coin buys less than it did before. The silver that was supposed to make Spain the wealthiest empire in history instead generated inflation that eroded real wages, destabilized governments, bankrupted merchants who had barred against stable prices that stopped being stable, and contributed to social upheaval across an entire continent. Spain itself, the nation that controlled the source, ended up declaring bankruptcy 4 times in the 16th century alone. The country with the most silver was also the country most damaged by having too much of it. This is the template for what economists call the resource curse, or Dutch disease, a flood of wealth that hollows out productive capacity and leaves the source country worse off. Now scale it up. Scale it up by a factor so large that the Spanish silver flood looks like a garden hose compared to a burst dam. And instead of one commodity, apply it to iron, nickel, cobalt, gold, platinum, iridium, and every other metal locked inside 16 Psyche. Apply it not to the economy of 16th century Europe, but to the integrated global economy of the 21st century, where commodity prices are set on electronic exchanges in milliseconds, where pension funds and sovereign wealth funds hold positions in metals futures, where entire national economies are structured around the assumption that the metals beneath their soil will continue to have the value they have today. What happens? Let us start with iron, because iron is the foundation. Everything else is built on iron. Steel is iron. Infrastructure is steel. Buildings, bridges, ships, cars, appliances, military equipment, the physical skeleton of industrial civilization is iron. The global steel industry produces roughly 1.9 billion tons of steel per year. The total iron ore mined globally each year is about 2.5 billion tons. The iron ore market is worth roughly $300 billion annually. It is one of the largest commodity markets on Earth, and its pricing affects the cost of essentially every physical object manufactured anywhere. 16 Psyche contains an estimated 10,000 quintillion kilograms of metal, the majority of which is iron and nickel. The entire iron ore mined by humanity across all of recorded history, every ton ever pulled from every mine on every continent since human beings first learned to smelt metal, is estimated at roughly 30 billion tons. 16 Psyche contains in iron alone a quantity that makes that number invisible. If you began returning iron from 16 Psyche to Earth at a rate of 1 billion tons per year, a rate 10 times current global iron ore production, you could sustain that rate for longer than human civilization has existed and not meaningfully deplete the asteroid. The supply is not large, it is not abundant. It is, for all practical economic purposes, infinite relative to demand. What does infinite supply do to price? Basic economics gives you the answer immediately and brutally. When supply approaches infinity and demand remains constant, price approaches zero. Not lower, not cheaper, zero, or close enough to zero that the difference is academic. The iron ore market, currently worth $300 billion a year, goes away. Not shrinking, goes away. The steel industry does not become less profitable. It becomes unrecognizable, restructured entirely around whoever controls the supply chain from asteroid to processed metal. With the mining and ore extraction phase eliminated entirely, every company that currently makes money pulling iron out of the ground stops making money. Every worker employed in iron ore extraction loses the economic rationale for their job. Every government that taxes iron ore production loses that revenue. Every infrastructure project that was budgeted around current steel prices has to be rebudgeted around a new price that nobody can yet calculate because it has never existed before. And this is just iron. Now do gold. The gold market is different from the iron market in a crucial way. Gold's value is not primarily industrial. Yes, gold is used in electronics, in medical devices, in various industrial applications. But the majority of gold's value comes from its role as a store of value, a financial asset, a hedge against inflation and currency instability, the physical embodiment of the idea that wealth can be made permanent and portable. This role depends entirely on gold being scarce. The entire history of gold as money, stretching back thousands of years, is a history of an asset whose value is inseparable from its rarity. All the gold ever mined in human history, every bar, every coin, every piece of jewelry, every circuit board trace, amounts to roughly 210,000 tons. It would fill approximately 3.7 Olympic swimming pools. That's it. That is the entire accumulated gold stock of human civilization. Its scarcity is what makes it valuable. Its scarcity is what makes it gold in the financial sense of the word. 16 Psyche is estimated to contain gold, not in the same proportion as iron and nickel, which dominate its composition, but in quantities that, brought to Earth, would make the total current gold stock look like a rounding error. If even a fraction of a percent of Psyche's mass is gold, which is consistent with estimates of planetary core compositions, the amount of gold involved is thousands of times larger than everything humanity has ever mined. The price of gold does not fall gradually in this scenario. It collapses. The entire financial architecture built on gold scarcity, the gold ETFs, the central bank reserves, the gold-backed instruments, the entire cultural and economic meaning of the phrase worth its weight in gold has to be rebuilt from scratch around an asset that is no longer rare. Platinum group metals tell a similar story with an additional twist. Platinum, palladium, rhodium, iridium, osmium, ruthenium. These 6 metals are among the rarest on Earth's surface, present in such small quantities that the entire annual global production of platinum is roughly 180 tons. Their rarity makes them extraordinarily valuable. Platinum trading at roughly $1,000 per troy ounce. Rhodium at various points reaching $30,000 per troy ounce, making it briefly the most expensive metal on Earth. They are also industrially critical in ways that have nothing to do with their financial value. Platinum group metals are the catalysts and catalytic converters that reduce vehicle emissions. They are essential components in fuel cells, in cancer treatments, in the electronics in your phone, in the industrial processes that produce nitric acid and other chemicals at scale. Their scarcity is not just a financial fact. It is a physical constraint on the rate at which certain technologies can be deployed. Asteroid mining advocates often argue this point as the most compelling economic case for the industry. The green energy transition requires enormous quantities of platinum group metals for fuel cells and electrolyzers. The supply is simply insufficient at current mining rates to support the transition at the pace that climate targets require. Asteroid mining solves this problem. It unlocks a supply of catalytic metals large enough to build all the fuel cells and electrolyzers and clean energy infrastructure the world needs, without being constrained by what can be pulled from. South African mines, which currently produce roughly 75% of the world's platinum. This argument is true as far as it goes. It just does not go far enough, because unlocking that supply also collapses the price of platinum, which collapses the economic incentive to produce it, which reshuffles the entire supply chain, which affects every economy that currently depends on platinum mining for revenue. South Africa produces 75% of global platinum. Its entire economic development model in the mining regions is built around the assumption that platinum is and will remain one of the most valuable metals on Earth. An asteroid mining operation that floods the market with platinum does not just reduce South Africa's mining revenues. It potentially removes the economic basis for entire regions of the country. Now extend this logic across the entire map of resource-dependent economies. Australia. The Australian economy is more dependent on iron ore exports than almost any other developed nation on Earth. Iron ore is Australia's single largest export, generating roughly $100 billion in export revenue annually. The Pilbara region of Western Australia is essentially an iron ore extraction machine at continental scale, with some of the largest mines ever built, operated by companies like BHP, Rio Tinto, and Fortescue, sending ore on trains that stretch for kilometers to ports where it is loaded onto ships bound primarily for China. The entire economic model of modern Australia, its high standard of living, its public services, its AAA credit rating, is partially underwritten by the assumption that iron ore will continue to be worth what iron ore is currently worth. If that assumption breaks, Australia does not become poor overnight. It becomes something more complicated, a wealthy country with a suddenly obsolete industrial heartland, facing the kind of structural economic adjustment that took decades and generated enormous political turbulence in the industrial regions of the United States and the United Kingdom when their foundational industries declined. The Democratic Republic of Congo, home to an estimated $24 trillion in untapped mineral wealth, including roughly 70% of the world's cobalt reserves, an element that is currently essential for lithium-ion batteries and therefore for electric vehicles and grid storage. The DRC's cobalt is mined under conditions that have generated sustained international criticism, including extensive use of child labor in artisanal mining operations and environmental damage of significant scale. The ethical problems with Congolese cobalt have driven significant investment in alternative battery chemistries that reduce cobalt dependence, and in asteroid mining is a long-term alternative source. But cobalt is also one of the metals that asteroid mining could deliver in quantity. If it does, the Congolese cobalt economy, already fragile and exploitive, loses its economic rationale entirely. The children working in the mines lose their income, which is not a clean win when the alternative is no income at all. In a country with insufficient social infrastructure to absorb the shock, Chile and Peru together produce roughly half the world's copper. Copper is not present in 16 Psyche in the quantities that iron and nickel are, but near-Earth asteroids of other compositions contain it in meaningful quantities. Chile's entire northern economy, the Atacama region, is essentially a copper extraction operation. The revenue funds schools, hospitals, infrastructure, the political economy of Chilean copper, including the nationalization debates that have occurred throughout the country's history, and the social conflicts around mining communities, is one of the defining features of Chilean political life. Disrupt the copper price and you disrupt something fundamental about how that society is organized. Venezuela, Russia, Saudi Arabia. These are the canonical examples of the resource curse. The well-documented economic phenomenon where countries with abundant natural resources tend to develop weaker institutions, more corrupt governments, less diversified economies, and worse long-term development outcomes than comparable countries without resources. The resource curse operates through several mechanisms. Resource wealth generates government revenue that does not require taxation, which weakens the accountability relationship between citizens and governments. It makes the currency strong, which makes other exports uncompetitive. It creates powerful interest groups organized around resource extraction who resist economic diversification. Countries that fall into the resource curse become structurally dependent on the price of one commodity. When that price rises, the government spends freely. When it falls, the crisis is immediate and severe because there are no alternative sources of revenue or employment to buffer the shock. Now imagine an asteroid mining operation that does not just reduce commodity prices, that eliminates them as meaningful economic variables. The resource-cursed countries, the ones that were already suffering from overdependence on resource revenues, face not a price downturn but an existential question about the economic basis of the state itself. Venezuela, whose economy collapsed catastrophically when oil prices fell in the 2010s, would face something qualitatively worse than what it has already experienced. Russia, whose federal budget depends on hydrocarbon revenues for roughly 40% of its income, would face a fiscal crisis of a kind that has historically preceded political instability of the most serious kind. The connection between resource revenue collapse and political instability is not theoretical. It is one of the most robust findings in the political science of development. None of this means asteroid mining is bad. The same technology that collapses commodity prices also, potentially, makes the physical inputs for building civilization dramatically cheaper. Steel at near zero cost means infrastructure in the developing world becomes affordable in ways it has never been. Platinum at near zero cost means fuel cells become cheap enough to deploy at scale in countries that currently cannot afford clean energy infrastructure. The metals that currently flow from poor countries to rich ones through mining operations of dubious ethical character could instead flow from space, eliminating the human cost of extraction entirely. The environmental damage from terrestrial mining, the habitat destruction, the toxic tailings, the water contamination that follows mining operations everywhere on Earth goes away along with the mines. But these benefits are not automatic. They do not distribute themselves evenly. They accrue first and most heavily to whoever controls the supply chain from asteroid to consumer. The countries and companies at the upstream end of the new supply chain capture the value. The countries whose economic model depended on the old supply chain are left to manage the transition on their own, with the same institutions and governance structures that the resource curse already weakened, now facing a shock larger than any previous commodity bust in history. History does not offer a single example of a massive commodity price collapse that resolved itself quickly and equitably. The transitions are long, painful, and politically turbulent. The people who suffer most are not the investors who saw it coming and repositioned their portfolios. They are the workers, the communities, the countries that were downstream in the value chain and had no agency over what happened upstream. The economists who think carefully about asteroid mining increasingly argue that the question is not whether it will happen. It will happen. The question is whether there's any mechanism, any international institution, any policy framework capable of managing the transition in a way that distributes the benefits more broadly than the extraction of terrestrial resources ever did. Whether humanity, confronted with the greatest single increase in material wealth in its history, can do something it has never done before with resource windfalls. Share it. The history of resource windfalls is not encouraging on this point. Every previous boom, every surge of previously unavailable wealth has concentrated in the hands of the people who are already positioned to capture it. The gap between those people and everyone else has reliably widened. The promise that wealth would trickle down, spread out, reach the communities and countries that bore the costs of extraction has reliably been broken. But this time, someone is making a different argument. Someone is doing the math in a different direction, not asking who captures the value, but asking what happens if you actually tried to distribute it, what the number looks like if you divide it not among shareholders and sovereign wealth funds, but among every human being alive on Earth. That math produces a number that sounds at first like pure fantasy, and then you do it carefully, and you realize it might not be fantasy at all. It might be the most important calculation anyone has ever done. Let's do the math. Right now, together, with no shortcuts and no rhetorical sleight of hand, because the math is the whole point and it deserves to be done honestly rather than impressionistically. The headline version, the version that generates the clicks and the YouTube thumbnails and the breathless articles, goes like this. 16 Psyche is worth $10,000 quadrillion. There are 8 billion people on Earth. Divide the first number by the second, and every human being gets approximately $1.25 billion. Every person on Earth, every subsistence farmer in Bangladesh, every child in the favelas of Sao Paulo, every elderly woman in rural Nigeria, every undocumented worker in California, every person alive right now, regardless of where they were born or what they own, becomes, on paper, a billionaire. Not a millionaire, a billionaire. The kind of wealth that, one generation ago, existed only in the fantasies of lottery winners and the actual bank accounts of a few hundred people globally. This is the number that makes the headline. This is the number that earns the video its views. Now let's talk about why it is, in its current form, almost entirely meaningless. And then, more interestingly, let's talk about the narrower version of the question that is not meaningless at all. The first problem with the headline math is the one we already visited in Part 5. The $10,000 quadrillion figure uses current Earth commodity prices. The moment you begin extracting those commodities and introducing them to the market, the prices collapse. If iron price drops to 1% of its current value, the iron component of Psyche's valuation drops to 1%. If gold collapses to the price of copper, the gold component collapses accordingly. The act of monetizing the asteroid destroys the valuation on which the headline number is based. You cannot divide $10,000 quadrillion by 8 billion people if extracting the asteroid reduces $10,000 quadrillion to $100 quadrillion or $10 quadrillion or some number. That is still enormous, but is not the number in the headline. The valuation is a snapshot of a world that ceases to exist the moment extraction begins. It is like pricing a painting at auction, then immediately reprinting 10 million copies and distributing them to every museum on Earth and wondering why the original is now worth less than you expected. The second problem is operational. The $10,000 quadrillion is not sitting in a vault somewhere, liquid and ready to distribute. It is locked in a spinning metallic asteroid 370 million kilometers away that no human has ever visited and no machine has yet touched in any meaningful way. Converting that potential value into actual value requires investment, technology, infrastructure, time, and risk of a kind that makes the most ambitious engineering projects in human history look modest by comparison. The Panama Canal took 10 years and killed thousands of workers. The Apollo program took a decade and cost in today's dollars roughly $280 billion. An asteroid mining operation capable of extracting material from 16 Psyche at industrial scale would require sustained investment and development effort that makes both of those projects look like proof of concept demonstrations. Before a single dollar of Psyche's value can be distributed to anyone, an enormous amount of money has to flow in the opposite direction, from investors to engineers to rocket manufacturers to spacecraft builders to mission operators. With no guarantee of success and every possibility of catastrophic failure at any of dozens of critical junctures, the third problem is political, and it is the deepest problem of all. Who decides how to distribute the proceeds? On what legal authority? Through what mechanism? Enforced by whom? The Outer Space Treaty says space is the province of all mankind. It does not say mankind has a legal claim on the revenue generated from space resources. It does not establish a distribution mechanism. It does not create an institution with the authority to collect proceeds and send checks to 8 billion people. The gap between the poetic principle that space belongs to everyone and the practical reality of who will actually control the supply chain and capture the value is not a small gap. It is the entire substance of the political challenge, saying space is the province of all mankind, while letting private companies incorporate under national laws and claim ownership of extracted resources is roughly equivalent to saying the ocean belongs to everyone and then letting fishing fleets from wealthy nations vacuum it clean, while subsistence fishermen in developing countries watch their food source disappear. The principle and the practice are not just different, they are opposite. So the honest answer to whether asteroid mining will make every person on Earth a trillionaire is no. The headline math does not survive contact with economics, engineering, or politics. The fantasy version of this story, the one where a rock in space is divided equally among humanity and everyone gets $1 billion, is not how resource extraction has ever worked at any point in human history. And there is no structural reason to believe it will work that way this time. But here is where it gets interesting. Here is where the honest version of the question, stripped of the fantasy, still produces an answer that should genuinely astonish you. You do not need to distribute $10,000 quadrillion equally to every human being on Earth to transform the human condition in a way that is historically unprecedented. You do not need the math to work out to $1 billion per person. You need something much more modest. You need the cost of the physical inputs of civilization, the metals that build infrastructure, the materials that manufacture technology, the commodities that determine how expensive it is to build a hospital or a school or a water treatment plant or a power grid, to fall dramatically, and that unlike equal distribution of asteroid wealth is something that asteroid mining could actually produce as a side effect of its own economics, regardless of any deliberate redistribution policy. Consider what cheap steel means. Not free steel, not asteroid flood of the market steel, just significantly cheaper steel. The reason that large parts of the developing world lack adequate infrastructure is not primarily a lack of will or governance capacity, though those problems are real. It is a lack of capital. Building a railway in sub-Saharan Africa costs roughly $5 million per kilometer, of which a significant fraction is the cost of steel and other metals. Building adequate housing for the 1.1 billion people currently living in slums globally requires steel, copper wiring, and structural materials. Building the water treatment infrastructure that could eliminate waterborne disease, which kills roughly 2 million people per year, requires pipes and pumps and tanks made of metal. The physical cost of building a decent civilization for everyone on Earth is enormous, partly because the raw materials are expensive, partly because pulling them out of the ground is difficult and damaging and controlled by entities who charge accordingly. If the raw material cost drops by 80%, the capital required drops by a meaningful fraction. Projects that were financially impossible become possible. Governments that could not afford infrastructure can afford it. The physical barrier to development, not the only barrier, but a real one, lowers. This is not the $1 billion per person fantasy. It is something quieter and more structural and potentially more transformative than cash transfers to individuals. It is the removal of a physical constraint on what civilization can build. But let's be honest about who captures the value before any of this diffuse benefit reaches ordinary people. Because there is a step in between the asteroid and the lower steel prices, and that step is the pipeline. The extraction, transportation, processing, and distribution infrastructure. And whoever owns the pipeline does not share its profits automatically or proportionally or equitably. They share them under whatever legal and political framework exists at the time. And the legal and political framework that currently exists is one that is very good at concentrating wealth in the hands of pipeline owners, the entities best positioned to win. SpaceX, Blue Origin, major aerospace contractors, and state-backed programs in China have every structural incentive to capture value, not automatically distribute it. This is not a moral judgment. It is a description of how large-scale capital operates. The new oligarchs of space will not look dramatically different from the old oligarchs of oil. They will be richer because the resource is bigger. They will be more technologically sophisticated because the extraction is harder. They will have better public relations because they will be associated with the romance of space exploration rather than the grimminess of oil drilling. But the structural position they will occupy, controlling a critical resource supply that everyone depends on, negotiating with governments from a position of irreplaceable importance, shaping the regulatory environment through lobbying and political influence, is the position that Standard Oil occupied in 1900 and Saudi Aramco occupied in 1970, and that pipeline owners have occupied in every resource economy ever constructed. There is a concept in economics called rent. Not the rent you pay for your apartment, though it is related. Economic rent is the return that accrues to the owner of a scarce resource beyond what would be required to induce them to supply it. If iron is worth $100 a ton and it costs $10 a ton to mine and deliver it, the $90 difference is rent. It flows to whoever owns the mine, not because they created the iron, not because they deserve it in any moral sense, but simply because they control access to something scarce that others need. Resource economics is the economics of rent, and the history of rent is the history of wealth concentration, because rent does not require you to do anything clever or productive. It requires you to own something and charge others to use it. Asteroid mining at scale would be the largest rent-generating enterprise in human history. Whoever controls access to 16 Psyche, or to the near-Earth asteroids that become the first commercial operations, sits in the position of a landowner whose land contains all the iron in the world. The rent they can charge is not limited by competition from other suppliers, because there are no other suppliers at that scale. It is limited only by what the market will bear, which in the case of metals that every industrial process on Earth requires, is a very large number indeed. The gap between that rent flowing to pipeline owners and that rent flowing to the 8 billion people whose labor and consumption ultimately generate the demand that makes the metals valuable is not a gap that closes automatically. It closes only under specific conditions, either competition, multiple independent suppliers driving prices toward cost, or regulation. Governments imposing taxes and redistribution mechanisms on the rent, or collective ownership, the supply chain being structured from the start as a commons rather than a private asset. Each of these mechanisms has historical precedents. Each has worked in some contexts and failed in others. None of them is guaranteed. The competition mechanism requires that the asteroid mining industry not consolidate into a monopoly or cartel in its early stages, which is precisely what industries with enormous capital requirements and first-mover advantages tend to do. The airline industry, the telecommunications industry, the social media industry, all sectors where network effects and capital barriers favor consolidation. Asteroid mining has both. The regulatory mechanism requires governments to impose meaningful taxes on space resource extraction and use the revenue for broad public benefit, which is what Norway did with its oil revenues, and what Nigeria did not. The difference being quality of institutions rather than quantity of resources. The collective ownership mechanism requires an international agreement to treat space resources as a global commons and distribute the proceeds accordingly, which requires exactly the kind of multilateral cooperation that the current geopolitical environment, characterized by intensifying US-China competition and the erosion of multilateral institutions, makes maximally unlikely. None of these mechanisms is impossible. Norway is a real country that really did use resource wealth to build the world's largest sovereign wealth fund, now worth over $1.7 trillion, generating returns that fund public services for every Norwegian citizen. The Alaska Permanent Fund really does distribute oil revenue dividends directly to every Alaskan resident, a form of universal basic income funded by resource extraction that has been running since 1982 and has paid out over $25,000 per resident over its lifetime. These are existence proofs that resource wealth can be distributed broadly rather than captured narrowly. They are small-scale, national examples, but they demonstrate that the mechanism is real and functional when the political will exists to implement it. The political will. That is always the variable, the constraint that does not appear in the engineering calculations or the economic models. The thing that determines whether the right answer and the actual answer converge. Political will is generated by power. Power in democracies is partially generated by organized citizens who understand what is at stake and demand specific outcomes. The asteroid mining industry is still young enough. The policy framework still unwritten enough. The outcomes still undetermined enough. The decisions being made right now, in congressional hearings, in international treaty negotiations, in corporate boardrooms and academic papers that inform both, will shape the structure of the industry for decades. The window for getting the incentives right, for building the redistribution mechanisms before the pipeline owners are too powerful to be taxed or regulated effectively, is open now. It will not stay open indefinitely. It never does. Because the pipeline owners understand this too. They are not passive actors waiting for governments to tell them what to do. They are active shapers of the regulatory environment, hiring lobbyists, funding think tanks, cultivating political relationships, framing the public conversation in ways that favor their preferred outcome. The framing they prefer is the innovation framing. Asteroid mining is progress. It is technology. It is the future. It is humanity reaching for the stars. And any attempt to regulate it or tax it or impose collective ownership requirements on it is Luddism, is holding back human potential, is letting the perfect be the enemy of the good. This framing is not entirely wrong. Innovation does require risk-taking and profit incentives and freedom from excessive regulatory burden, but it is also not the whole story. And the parts it leaves out are precisely the parts that determine whether the benefits are distributed broadly or concentrated narrowly. The math of distribution is not just arithmetic. It is politics. It is history. It is the question of whether the institutions that govern human societies are capable of responding to a challenge that has no precedent in speed, scale, or complexity. Whether the people who write the rules can think clearly about a future that feels abstract and distant when the decisions are being made, but will be concrete and immediate and irreversible when the ships are actually flying. The trillionaire equation does not have a numerical answer yet, not because the math is unclear, but because the political variable is unsolved. The number that every human being on Earth ultimately receives from the wealth of 16 Psyche, whether it is 0 or $1,000 or 1,000,000, will be determined not by physics and not by economics, but by choices. Choices being made right now by people who mostly have not framed them as choices about asteroid mining at all, but as choices about space law and corporate taxation and international institutions and the appropriate role of government in emerging industries. These are not exciting choices. They do not generate the kind of headlines that a $10,000 quadrillion asteroid generates. But they are the choices that actually matter. The choices that determine whether the oldest pattern in human history, enormous wealth discovered, enormous wealth captured by whoever got there first, repeats itself one more time in a new setting, or whether something different happens. History says the pattern repeats. But history has been surprising before. The last time it was surprising, it was because people who understood what was at stake refused to accept that the pattern was inevitable. They organized. They demanded different rules. They built institutions capable of enforcing those rules. They did not always succeed. They often failed. But sometimes, in enough places and enough circumstances to matter, they changed the outcome. What they were fighting against, in every previous case, was not physics and not economics. It was the argument that the way things have always gone is the way things must go, that the powerful capturing the wealth of new frontiers is natural, inevitable, and ultimately beneficial, because at least someone is developing the resource rather than leaving it untouched. You will hear that argument made about asteroid mining. You are probably already hearing versions of it. It will be made fluently and confidently by intelligent people with good data and compelling presentations and genuine belief in what they are saying. Whether you find it convincing depends on what you think history actually teaches. And history, on this point, has a great deal to say. Not all of it is about economics. Some of it is about what happens when the people making the argument that this time is different, that this boom will spread its benefits more broadly, that the wealth will trickle down, have been wrong before, repeatedly, systematically, in ways that generated consequences measured not in percentage points of GDP, but in decades of suffering for the people who were downstream when the pipeline owners finished building the pipeline. That history is where we are going next, because the most important thing asteroid mining can teach us is not about space. It is about what we have already done on Earth with every previous frontier, what we got right and what we got catastrophically wrong, and whether we are capable as a species of learning the lesson before we are in a position where the stakes are too high and the window too narrow to apply it. That story has been playing out for 500 years and is not finished yet. We have already seen this pattern play out on Earth, from Spanish silver to Nigerian oil and Venezuelan collapse. The mechanism is always the same. Start in Spain, because Spain is the canonical example of a country that won the resource lottery and then lost everything that mattered. In 1492, the year Columbus sailed, Spain was a middling European power. Its economy was agricultural. Its military was competent but not dominant. Its position in the emerging global order was promising but not yet exceptional. What changed everything was not genius or virtue or the superior organization of Spanish institutions. What changed everything was geographic luck. The accidents of ocean currents and wind patterns that made the western route across the Atlantic navigable, combined with the technological advantage of ships and guns, and the catastrophic biological accident of old world diseases encountering new world populations with no immunity to them. Within decades, Spain controlled the largest empire the world had ever seen. Within a century, silver was flowing from Potosi and from the mines of Mexico in quantities that had no precedent in human history, and it destroyed Spain, not immediately, not dramatically, but systematically and irreversibly, in the way that cancers destroy rather than the way that bullets do. The mechanism was inflation. When silver floods an economy that has not increased its production of actual goods, each unit of silver buys less. Prices rise. Real wages, the purchasing power of what workers are paid, fall even as the nominal numbers increase. The Spanish economy, flooded with silver revenue, experienced a price revolution that made domestic manufacturing uncompetitive. Why build things at home when silver from the colonies can buy them cheaper from England or France or the Dutch Republic? The industrial capacity that might have made Spain a durable power was hollowed out. The artisans and manufacturers who might have built it went out of business, displaced by cheaper imports paid for with colonial silver. Spain became a country that extracted wealth from one part of the world and spent it on goods produced in other parts of the world, enriching its competitors while neglecting its own productive capacity. This is not ancient history. This is a pattern so well documented that economists gave it a name in the 20th century when they watched it happen again, in real time, in country after country. The Dutch disease, named after the experience of the Netherlands in the 1960s, when the discovery of North Sea natural gas caused the Dutch currency to appreciate sharply, making Dutch manufacturing exports uncompetitive and hollowing out the industrial sector even as the gas revenue poured in. The mechanism was different from the Spanish case. The result was the same. A sudden influx of resource wealth distorted the economy in ways that damaged productive capacity and created long-term vulnerabilities that outlasted the resource boom itself. The Dutch got off relatively lightly, partly because their institutions were strong enough to manage the transition, and partly because the damage was limited to manufacturing competitiveness rather than extending to total economic collapse. Other countries have not been so fortunate. Nigeria discovered oil in 1956. By the 1970s, it was one of the most promising economies in Africa, with oil revenue funding infrastructure, education, and the beginnings of industrial development. Today, after 50 years of oil wealth, Nigeria has the largest economy in Africa by GDP and one of the highest rates of extreme poverty. The oil revenue, rather than distributing broadly, flowed through a political system that the oil wealth itself had corrupted. Controlling access to oil revenue made political power extraordinarily valuable, which made the competition for political power extraordinarily violent, which created the conditions for military coups, civil war, institutional decay, and the systematic looting of public funds by whoever happened to hold office. The oil did not cause this directly, but it created the conditions in which the worst tendencies of human political behavior were amplified to their maximum destructive potential. The resource curse does not work by making bad things happen. It works by making bad things much worse than they would otherwise have been. Venezuela is the freshest example, close enough in time that the wounds have not yet scarred. In 2001, Venezuela had the highest standard of living in Latin America. Its oil reserves, the largest proven reserves of any country on earth, seemed to guarantee a prosperous future. Today, Venezuela has experienced one of the largest non-wartime economic collapses in modern history. Hyperinflation has destroyed savings. Basic goods have become unavailable. Over 7 million people, roughly a quarter of the population, have fled the country. The oil did not cause this either, but when the political institutions responsible for managing the oil revenue broke down, when the government that had structured the entire economy around oil price assumptions faced a sustained price collapse, there was nothing else. No alternative industries, no diversified tax base, no economic resilience of any kind. The broom had crowded out everything that might have survived the bust, and here is the point that connects this history to 16 Psyche in a way that is not merely analogical, but structural. Every one of these cases, Spain and its silver, Nigeria and its oil, Venezuela and its petrostate, the Democratic Republic of Congo and its minerals, the pattern is identical at the level of mechanism. A sudden access to enormous wealth from a resource that requires relatively little human ingenuity to extract, combined with institutions that are either too weak to manage the windfall or too captured by it to serve the broader public interest, produces outcomes that are catastrophically worse than having no resource at all. The resource is not the problem. The relationship between the resource and the institutions is the problem, and the institutions that are weakest, most captured, most likely to fail the test, are precisely the institutions in the countries that are most dependent on commodity revenue, which are precisely the countries that will be most devastated when asteroid mining eliminates the commodity revenue on which they depend. But there is a second dimension to this history that is less discussed and more disturbing. The countries that got rich from previous resource frontiers did not just benefit from the resources themselves. They benefited from the entire structure of control built around the resources. The trading companies that ran the colonial silver trade were not just mining silver. They were operating a system of extraction that pulled wealth from one part of the world and concentrated it in another, and the system was designed with the explicit purpose of maintaining that concentration. The oil companies that developed the Middle East fields in the early 20th century were not just drilling for oil. They were constructing a political economy, drawing borders, installing governments, suppressing competitors, and building a supply chain architecture that ensured the value accrued at the downstream end in the refineries and petrochemical plants and consumer markets of the wealthy world, rather than at the upstream end, in the countries whose land the oil happened to be under. The people who design the legal frameworks for space resource extraction are aware of this history, at least some of them. The Outer Space Treaty's declaration that space is the province of all mankind was precisely an attempt to prevent the colonial pattern from being replicated in space. It was written in 1967 by people who had watched the decolonization of Africa and Asia, and who understood, at least in principle, that the structure of resource control was not separable from the structure of political domination. They were trying to write a rule that would prevent a new form of colonialism from taking root in the one frontier that no existing nation had yet claimed. They did not succeed, not because the principle was wrong, but because the principle was not backed by enforcement. The Outer Space Treaty created an aspiration. It did not create a mechanism, and in the absence of mechanisms, history tends to default to the pattern that powerful actors find most convenient, which is also, by an extraordinary coincidence, the pattern that powerful actors have already implemented and therefore have the institutions and infrastructure to perpetuate the race to write national space resource laws. The American Commercial Space Launch Competitiveness Act, Luxembourg's space resources legislation, the UAE framework, and all the others, is not a race to honor the principle that space is the province of all mankind. It is a race to carve up the province among the nations whose companies are most likely to get there first. The laws are written in the language of innovation and economic freedom. They are structured to produce outcomes that look remarkably like the outcomes of every previous resource frontier, with the caveat that the distances involved are greater and the PR is better. Look at what happened with deep-sea mining. The United Nations Convention on the Law of the Sea, finalized in 1982, established that the resources of the deep seabed, beyond any national jurisdiction, were the common heritage of mankind. It created an institution, the International Seabed Authority, to manage those resources on behalf of all nations. It established a system where mining companies would pay royalties that would be distributed to developing nations, explicitly to prevent the pattern of resource extraction benefiting wealthy countries at the expense of poor ones. This framework took decades to negotiate and represented a genuine attempt to apply the lesson of colonial resource extraction to a new frontier, and it has never worked as intended, because the wealthy nations whose companies were most capable of deep-sea mining never accepted the full framework, because the technology to make deep-sea mining commercially viable has developed faster than the governance structures designed to regulate it, and because the institutional capacity of the International Seabed Authority to actually enforce its mandate against companies backed by major powers is, to put it gently, limited. Space is not the deep sea. It is harder to reach, which means the early actors are fewer and more visible. But it is also harder to regulate, because there is no physical presence of enforcement authority that can be deployed to an asteroid 370 million kilometers from Earth. If a company lands on a near-Earth asteroid and begins extracting platinum group metals, and that company is backed by a nation that disagrees with whatever international framework nominally governs the activity, the options for enforcement are primarily diplomatic rather than physical. Diplomacy, in a world where the major space powers are engaged in intensifying strategic competition, is not a robust enforcement mechanism. The relevant historical warning is not just that resource booms are followed by busts. That is true but incomplete. The relevant warning is that the structure of control established during the boom phase, who owns the pipeline, who wrote the rules, whose legal framework governs the disputes, becomes self-reinforcing in ways that are extraordinarily difficult to reverse after the fact. The oil companies that developed the Persian Gulf fields in the 1940s and 1950s wrote contracts that were so favorable to themselves and so unfavorable to the host nations that they became the cause of nationalizations and coups and wars. Because the only way to renegotiate a contract written by the powerful for their own benefit is through force. The nations that colonized the silver trade of the Americas did not voluntarily relinquish their control when the moral argument against it became clear. They relinquished it when the cost of maintaining it exceeded the benefit, measured in military expenditure, political instability, or when the resource ran out. The lesson is not that history always repeats. The lesson is that history repeats unless something specific interrupts the pattern. Not good intentions. Not philosophical arguments about what is fair. Something structural. An institution with genuine enforcement power. An economic arrangement where the incentives align with broad distribution rather than narrow capture. A political movement capable of overcoming the organized resistance of the entities whose wealth depends on the existing arrangement. None of those things currently exist in the domain of space resource extraction. Some of them are being built slowly and incompletely by people who understand the history and are trying to apply its lessons. Whether they are built quickly enough and with enough genuine authority to interrupt the pattern before it becomes self-reinforcing is the most important institutional question of the next 20 years. It does not sound like the most important question because it is couched in the dry language of treaty negotiation and regulatory design and corporate law. It does not generate the emotional response that a spinning metallic asteroid worth $10,000 quadrillion generates. But those institutional questions, answered well or badly, will determine whether the enormous potential of asteroid mining generates the largest and most broadly distributed increase in human welfare in history, or whether it generates the largest and most brutal concentration of wealth and power ever seen. History is watching. It has seen this before. It knows exactly how the story usually ends. The question is whether we do too. There is a thought experiment that philosophers sometimes use to probe the assumptions built into our moral intuitions. Imagine a world without scarcity, not just abundant, not just wealthy, but genuinely, structurally without scarcity. A world where the physical inputs required to sustain human life and human civilization are so plentiful that the question of who gets what ceases to be a zero-sum competition and becomes instead a question of organization and preference. What does justice look like in that world? What does politics look like? What does war look like? What does it mean to be human in a world where the oldest and deepest source of human conflict has been removed? This thought experiment has always been exactly that. A thought experiment, a philosopher's exercise in moral reasoning from impossible premises. Because in every world that has ever actually existed, scarcity has been the bedrock condition. There has never been enough. There has never been enough food, enough water, enough land, enough metal, enough fuel, enough of whatever the civilization of the moment most required. The entire history of human social organization, of property rights and laws and governments and armies, is an elaborate answer to the question of what to do when there is not enough for everyone, and someone has to decide who gets what. 16 Psyche does not answer that question. Not completely. Not immediately. Not even close to immediately. But it does something that no previous discovery in human history has done. It makes the question answerable in principle. It establishes, for the first time in the life of our species, that the constraint of not enough is not a permanent feature of our existence, but a contingent one, a function of where we have been looking, not a reflection of what the universe actually contains. That is a philosophical earthquake, even if its physical effects will be felt slowly and unevenly, and with all the complexity and injustice that the preceding chapters of this story have laid out in careful detail. Let's sit with it for a moment before returning to the complications. For 300,000 years, our species evolved under permanent scarcity. Our instincts, institutions, and moral intuitions were all shaped by the reality of not enough. What happens to a species shaped by scarcity when scarcity begins to dissolve? Nobody knows, because it has never happened before, not at this scale, not to this degree. The agricultural revolution reduced food scarcity in some places for some people, enough to allow civilization to emerge. The Industrial Revolution reduced scarcity of manufactured goods dramatically, enough to produce the material conditions for modern life as most people in wealthy countries currently experience it. But neither revolution eliminated scarcity at the fundamental level. Both created new forms of scarcity alongside the old ones. Both operated within a world where the total supply of raw materials remained fixed and finite, where every gain in one place came at some cost somewhere else, where the zero-sum character of resource competition never fully dissolved, even as the specific resources being competed over changed. Asteroid mining at scale changes something more fundamental. It does not just reduce the cost of metals, it decouples human civilization from the specific geological accidents that currently determine who has what. Right now, the fact that Chile sits above the Atacama lithium deposits matters enormously to the global economy and therefore to global politics. The fact that South Africa's geology produced the Bushveld igneous complex and its platinum concentrations matters. The fact that the Congo's ground happens to contain cobalt matters. The accident of where specific metals ended up after the formation of the Earth 4.5 billion years ago determines, in significant ways, the political and economic relationships between nations today. Nations go to war, impose sanctions, negotiate treaties, and structure their foreign policies in response to the geological lottery of where the stuff ended up. If the stuff can come from space, the geological lottery loses its political force, not immediately, not smoothly, not without enormous disruption in the transition, but eventually, structurally, irreversibly. The location of copper deposits on Earth stops being strategically important when copper can come from near-Earth asteroids. The leverage that resource-rich nations have over resource-poor ones dissolves. The economic rationale for controlling trade routes to mineral-producing regions diminishes. Some of the most persistent sources of geopolitical tension in the modern world are, at their root, disputes over access to physical resources. Contested maritime territories in the South China Sea are contested partly because of the mineral and energy resources beneath the seabed. Middle Eastern conflicts are inseparable from the fact that the region sits atop a third of the world's proven oil reserves. If those resources become less important because better alternatives are available, the strategic logic that drives the conflict weakens. This is not a naive argument that asteroid mining will bring world peace. It is a structural argument that removing or reducing the physical scarcity that drives some forms of conflict reduces the incentive for those forms of conflict. War is rarely purely rational, rarely purely about resources, and eliminating the resource justification does not eliminate the tribalism and ideology and historical grievance and political miscalculation that also drive it. But scarcity reduction does eliminate some of the most concrete material reasons why states have historically found it rational to use force against each other. That is not nothing. That is, in fact, historically significant. Consider what the reduction of food scarcity did. The agricultural revolution did not end violence. It created new forms of it, including the conquest and enslavement that accompanied agricultural empires. But it did eliminate the specific form of violence driven by direct competition for hunting territories and foraging grounds. The Industrial Revolution did not end poverty. It created new forms of it, including the industrial immiseration that characterized early capitalism. But it did eliminate or drastically reduce some of the most direct forms of resource scarcity that had plagued pre-industrial populations. Each reduction in the baseline level of scarcity has been accompanied by suffering and injustice and new forms of exploitation, and each has also, over time, expanded the space in which human beings can pursue lives that are not entirely organized around survival. Asteroid mining, if it develops in a way that actually reduces the cost of physical civilization, adds another step in that sequence. Not the final step, because there is no final step, but a real step, with real effects on the conditions under which human beings live. Now here is where it gets genuinely strange, where the philosophical implications extend beyond economics and politics into something that touches the deepest questions about what it means to be human. Scarcity does not only drive conflict, it also drives creativity. The necessity that is the mother of invention is the necessity created by not having enough. Human ingenuity has been, for most of its history, directed primarily at the problem of getting more from less. Agriculture is an answer to scarcity. Trade is an answer to scarcity. The entire scientific and technological enterprise, at its root, is a systematic effort to extract more value from finite resources, to do more with less, to convert the things we have into the things we need. The drive to innovate is inseparable from the pressure of scarcity, because in a world of genuine abundance, the urgency that has historically driven innovation toward its most productive application simply does not exist in the same way. This is not an argument against abundance. It is an observation about the character of the transformation. The species that developed its capabilities under the pressure of scarcity and then found itself in a world of material abundance would not just be the same species with more stuff. It would face a genuinely new challenge, one that has no precedent in the evolutionary or cultural history of the organism. What do you optimize for when the optimization problem of survival has been solved? What do human social structures look like when they no longer have to solve the problem of distributing scarce resources? When the primary function of government and law and property rights, allocating insufficient goods among competing claimants, becomes less urgent? The optimistic version of this future looks like a world where human creativity, freed from the pressure of material survival, turns toward the problems that scarcity has always prevented us from solving. The great unsolved problems of medicine. The diseases that kill primarily because the resources required to address them are insufficient relative to demand. The environmental crises that persist partly because the short-term cost of addressing them seems prohibitive. The educational gaps that perpetuate poverty across generations, not because we lack knowledge about how to teach children, but because we lack the physical and financial infrastructure to do it at scale. The care work, the raising of children and the tending of the elderly and the support of the disabled that is currently undervalued and underprovided because the economic system we built under scarcity does not know how to price it adequately. If the physical inputs of civilization become dramatically cheaper, if the steel and copper and platinum and nickel that underlie industrial and technological society flow from space in quantities that make their price approach the cost of extraction rather than the value of scarcity, then the capital freed from the business of pulling metals out of the ground and distributing them through complex supply chains to end users could, in principle, be redirected toward these unsolved problems, not automatically, not without political struggle, not without the kind of redistribution mechanisms that history suggests will be fiercely resisted by the entities currently capturing the value of scarcity. But in principle, as a possibility that did not exist before, because the resource was genuinely insufficient, not just inequitably distributed, the pessimistic version is equally plausible and has more historical support. In the pessimistic version, the abundance generated by asteroid mining is captured by the entities that already have the most, reinforcing and accelerating the concentration of wealth and power that has characterized every previous resource frontier. The new oligarchs of space are so powerful, so entrenched, so structurally protected by the legal and political frameworks they helped write, that the potential benefits of abundance never actually reach the people for whom they were theoretically available. The wars that asteroid mining could have prevented are replaced by new wars, fought over control of the supply chains from space rather than control of the mines on Earth. The creativity that might have been freed from the pressure of scarcity is instead directed toward the new forms of competition that abundance generates. The struggle for status and meaning and identity in a world where material survival is no longer the organizing challenge, but something must fill its place. History does not adjudicate between these versions. History offers examples of both. The printing press was a technology of abundance, an abundance of information and ideas, and it produced the Renaissance and the Reformation and the scientific revolution, and also the religious wars that killed a third of the population of Central Europe and the propaganda machinery that enabled totalitarianism in the 20th century. The same technology, liberating and terrifying depending on the political and social context into which it was released. The internet repeated this pattern with eerie precision, promising democratic access to knowledge and delivering also surveillance capitalism and algorithmic radicalization and the infrastructure of authoritarian information control. Technologies of abundance are not inherently progressive or regressive. They are accelerants. They accelerate whatever tendencies already exist in the social and political order into which they arrive. Asteroid mining as an abundance technology will accelerate. The question is what it will accelerate, whether it arrives in a world that has managed to build institutions capable of distributing its benefits broadly, or a world that has failed to build those institutions and therefore has no mechanism to prevent its benefits from concentrating narrowly. This is why the institutional questions that seem boring and technical are in fact the philosophical questions. The questions about who writes the space resource laws and what mechanisms they include for redistribution are not administrative details. They are the questions that will determine whether the abundance of space is used to expand the possibilities of human life for everyone, or to expand the power of the people who are already most powerful. Whether the dissolution of material scarcity opens up new forms of human flourishing or simply creates new forms of competition for the status goods that scarcity-based thinking produces even in the absence of actual scarcity. There is a word that appears in discussions of post-scarcity futures that deserves more serious attention than it usually receives. The word has meaning. In a world where material survival is the organizing challenge, meaning is relatively easy to find. The work of staying alive, of feeding children and building shelter and maintaining the physical conditions for continued existence is meaning enough. It is a brutal meaning imposed by necessity rather than chosen in freedom, but it is meaning nonetheless. When that necessity diminishes, the question of meaning becomes more complex and more urgent. What do you do when you do not have to do anything in particular? What do you value when the market no longer tells you what to value? What do you become when you are no longer defined primarily by the work required to survive? These are not rhetorical questions. They are questions that wealthy societies are already grappling with, in forms that range from the epidemic of purposelessness documented in mortality statistics among working-age men in deindustrialized regions to the philosophical ferment around effective altruism and long-termism among people whose material needs are thoroughly met and who are therefore free to worry about entirely different problems. The post-material questions are not easier than the material ones. In some ways they are harder, because the material questions have at least the clarity of urgency, the unambiguous demand of hunger or cold or danger. The post-material questions have the complexity of freedom, the difficulty of choosing direction when the world is not compelling in any particular direction. A civilization that gains access to the material abundance of 16 psyche will not automatically become a better civilization. It will become a wealthier civilization, and wealth has historically been both a tool for human flourishing and an obstacle to it, depending on how it is organized and distributed and what values it is used to pursue. The new world that asteroid mining could create is not a solved world. It is a world with a new set of problems, some of which are more interesting than the old problems, some of which are more dangerous, and all of which will require the full application of whatever wisdom humanity has managed to accumulate over the 300,000 years we have been trying, imperfectly and often catastrophically, to figure out how to live together. What does it mean to be human when the oldest reason we have ever fought, not enough, begins to dissolve? It means the same thing it has always meant, and it means something entirely new. We are the species that has always found new reasons to fight even as old reasons disappeared. We are also the species that has always found new reasons to cooperate, new forms of solidarity and creativity and connection, even under conditions of scarcity that should, by a purely economic logic, have made cooperation impossible. We are neither the purely competitive animal of libertarian mythology, nor the purely cooperative being of utopian fantasy. We are something more complicated and more interesting than either. We are an animal that contains both, that has historically oscillated between them, and whose oscillations have been shaped in part by the material conditions in which they occurred. Change the material conditions dramatically enough, and you change the range of the oscillation. You do not determine the outcome, you expand the possibility space within which outcomes can occur. The most optimistic reading of 16 Psyche is not that it will make everyone rich. It is that it will expand the range of what is possible for human civilization, and that within that expanded range there are futures available that were not available before. Futures in which the resources required to address our deepest and most persistent problems are genuinely sufficient. Futures in which the question is not whether we can afford to solve the problem, but whether we have the wisdom and the will to solve it. Whether we move toward those futures or away from them depends on choices that are being made right now, mostly by people who have not framed them as choices about the future of human civilization. They have framed them as choices about space law and corporate structure and launch vehicle development and treaty interpretation and regulatory design. Technical choices, legal choices, financial choices, the choices that look small and procedural and boring in the moment and only reveal their true significance in retrospect, when the pattern has crystallized and the window for changing it has closed. History is not destiny. That is the only genuinely optimistic thing that can be said with confidence about the situation we are in. The pattern that has repeated in every previous resource frontier is not a law of nature. It is a consequence of choices made by people who were responding to the incentives and constraints of their moment, constrained by the institutions and ideas available to them, but choosing nonetheless. Different choices made by people who understood more clearly what was at stake and were capable of acting against their immediate self-interest in service of a longer-term vision, have sometimes produced different outcomes. Not often, not reliably, but sometimes. Somewhere in the darkness between Mars and Jupiter, 16 Psyche continues its silent orbit. It does not know we exist. It does not care. We are on our way, first in awareness, then in machinery. The conversation about what kind of humanity arrives there has already begun. The window is still open. What we do with it will reveal more about who we truly are than anything we have done before.